Welcome. In this video, we're going to talk about orbital diagrams and what kind of information they can give us. So at this point, you've learned how to write orbital diagrams and electron configurations, and you might be wondering, why would I want to do that, right? Are these useful? What kind of information do these tell us? And orbital diagrams do tell us some useful things. One of the main things that they show us is information about the unpaired electrons. And unpaired electrons will impact several things, including bonding and whether a substance is magnetic. So with bonding, the number of unpaired electrons will impact the number of covalent bonds an atom will form, and the ion charge when they form an ionic bond. So if we look at these examples down here, oxygen, we notice, has 2 unpaired electrons, and when it forms an ionic bond, it tends to form a -2 ion. And when it does covalent bonding, it tends to form 2 covalent bonds. So what happens is in an ionic bonding, an oxygen atom will tend to gain 2 electrons to fill up this subshell. And when it does covalent bonding, it's got these 2 unpaired electrons that are available to pair up with electrons in another atom to form bonds. Fluorine has 1 unpaired electron, and when it forms ionic bond, it tends to make a -1 ion. And in covalent bonding, it tends to form 1 covalent bond. If you look at neon and the other noble gases, they have no unpaired electrons, and so they tend to not form ions and not form covalent bonds because their electrons are all paired already. So the unpaired electrons are really useful to look at. Another thing that the unpaired electrons will impact is something called magnetism. And so a substance can either be paramagnetic or diamagnetic. And paramagnetic, a substance will be paramagnetic if they're unpaired electrons. A substance will be diamagnetic if all of its electrons are paired up. And what it means to be paramagnetic is it's attracted to a magnetic field. Okay, diamagnetic is going to be very weakly repelled by a magnetic field, and the up and down spins basically cancel each other out. So remember earlier we mentioned this idea of spin and that the electrons behave as if they're spinning, and the reason why we think this is because we can observe this kind of weak interaction with a magnetic field. So it turns out when you have a bunch of electrons all spinning in the same direction, then the substance will basically appear magnetic. It will be attracted to a magnetic field. If you have up and down spins canceling each other out, it'll behave as if it's not magnetic. And the things that we typically think of as magnets, like that we might use in our fridge, that's an example of what we call ferromagnetism. And that's the strongest form of magnetism. And that will happen, that's also what we call a permanent magnet. And this can happen in things like iron and cobalt and nickel. And what happens with ferromagnetism, with these permanent magnets, is that the unpaired electrons in all the adjacent atoms are spin aligned in the same direction. So that's a little something about magnetism. We don't need to worry about the details of that too much unless you're interested. Feel free to dig into that some more. The other thing we want to talk about is the noble gas shorthand. And so this is a nice kind of shortcut we can use when writing electron configurations of elements that have a lot of electrons in them. And so what we do is we use the electron configuration of the previous noble gas in brackets to represent as like a little shortcut here. So for example, magnesium has this electron configuration, 1s2, 2s2, 2p6, 3s2. Instead of writing out this whole thing, we can say, oh look, 1s2, 2s2, 2p6, that's the same as neon. Okay, and neon's a noble gas. And so as a shorthand, we can say magnesium is like neon with 2 more electrons in the 3s. And the reason why this is a useful shortcut is because it tends to be those outer electrons that are the ones that are reactive and determine the properties of a substance. So these core electrons in the middle, we tend to not care about as much, so we can kind of maybe fudge the details and not worry about them as much. So magnesium, it's like neon, but there's 2 outer electrons in the 3s. So there is an example I got from the previous page. And again, why do we do this? Well, it's shorter, right? It's a nice convenient shorthand because it can be a pain to write out the whole electron configuration for something like, mercury or lead that's got a lot of electrons in it. And the core electrons tend to not be as reactive, so this version tends to really focus us on those outer electrons there. So some practice, if we're running the noble gas shortcut here, if you're looking at potassium on your periodic table, potassium is element 19. And so the previous noble gas is argon. And so for potassium, what I could do is I could say potassium is like argon, but with 1 electron in the 4s. As argon is element 18. So basically the first 18 electrons look just like argon, and then the 19th electron is over here in the 4s. Tin is element number 50. The previous noble gas to tin is, if you look on your periodic table, it is krypton, which is element 36. So to write the electron configuration for tin, we could say, okay, the first 36 electrons look like krypton, okay? And then if we follow our pattern, electrons 37 and 38, they're going to go in the 5s. And then the next 10 electrons go in the 4d. And then the next 2 electrons go over here in the 5p. So instead of writing out all 50 of them, we're just using like a shortcut for those first 36 electrons and saying, oh, they just look like krypton. Okay. So there we go. And then mercury, if you find mercury, where is it? Mercury has 80 electrons. So that would be a lot to write out the entire electron configuration for mercury. And you should be able to do that, and that's something you can practice. But this is something we can use our noble gas shortcut for. So if we look at the previous noble gas, I'm going to call that PNB. Okay, previous noble gas that comes before mercury is xenon, which is element 54. So when we write the electron configuration of mercury, we're going to say, okay, those first 54 electrons look like xenon, so we're going to just write Xe in brackets. And then the next 2 electrons go in the, let's see, 5, 6, that's in row 6, so it's 6s2. And then careful, in the 6th row, that's where we get the F block involved. So what comes next is 4f, and that what comes after that is 5d. So here's the electron configuration of mercury, and this is much faster than writing out all 80 electrons. All right, so thanks for watching. Hope this helps. Let me know if you have questions.